Hello students. In today's lecture we are going to start unit 5, which is about the piping instrumentation. The first topic of this unit 5 will be the final control elements. So in a process plant piping system, the instrumentation and final control elements will play a major role in monitoring and controlling the process parameters to ensure the safety, efficiency and product quality. In a process plant, we need to monitor and regulate the flow control, then pressure control, level control, and the temperature control. So, the purpose of the instrumentation will be to first monitor or measure the process parameters. So, by process parameters, what do we mean is the flow, pressure, temperature, level, concentration, etc. Then we need to control or regulate the variables by using the feedback loops or the control loops. It is not necessary that we have only the feedback loops. We can also go for advanced control strategies and like your cascade control or your feed forward control, ratio control and so on. The purpose of instrumentation is to regulate the variables using the various feedback loops. Then we need to go for the automation, that is reducing the manual intervention and improve the efficiency of the process by going for automation. The current trend in the industries is moving towards automation. Earlier it was industry 4.0 and now the industry is now changing towards industry 5.0. 4.0 is the use of automated control loops and SCADA systems and PLC systems. SCADA means supervisory data acquisition and control, and PLC stands for your programmable logic controller. By using this automated devices, the data collection and the controls were being implemented in an automated way. Now the industry is slowly moving towards AI based control systems and cloud and IoT based control systems, where all the data and everything is stored in the cloud, and we can operate the process plant from sitting remotely in any part of the globe. So now the industry is moving towards such trends, and the next purpose of instrumentation is safety and protection. The safety and protection is when we are running a process, we have to look at the safety of the operating personnel, and the safety constraints will help us to reduce the lost man hours due to accidents, and it will prevent the process upsets, leak or overpressure conditions, so that the process is running in a safe manner. If we do not pay attention to the safety, then what happens is the loss of material and loss of life, and it may lead to some accidents. So the instrumentation prevents the process upsets, leaks or any overpressure conditions which may be harmful for running the process. Next is the data collection and analysis. If we want to collect the data in all the process piping, then we require certain instrumentation for collecting all the data. So if we need to optimize a process and troubleshoot, then we require the data on the flow, pressure, temperature, level, concentration. That is, we require the data on the process parameters so that we can analyze the data for process optimization and troubleshooting. In a process plant, it is necessary that we have to optimize the process parameters. Otherwise, we will not be running the plant in an efficient manner. So the resources that are used for the production has to be optimized so that the operating cost is reduced. That will indirectly lead to the savings in the operating cost. so that the return on investment is easily achieved in a shorter time span. So, and also the process optimization will help in getting a better yield or the better quality of the product, and it will also help in the various troubleshooting, that is the debottlenecking operations. So, the purpose of instrumentation also serves for data analysis and collection. To recap, the purpose of instrumentation will serve for monitoring, that is, it will measure the process parameters, then it will regulate the variables using various control loops or the feedback loops or any advanced control strategy loops. Then it will also serve for the automation and the safety and protection, data analysis and collection. So in piping instrumentation, we look at this table to understand the various common instruments that will be used for measuring a process variable. So if we consider flow to be the process variable, the common instruments that are used for measuring the flow are the orifice plate, then venturi meter, vortex flow meter, then Coriolis flow meter, then ultrasonic flow meter. The working principle of these common instruments will be, in the case of orifice and venturi meters, it is to measure the differential pressure. In the case of vortex flow meter, we have to measure the vortex shedding. In the case of ultrasonics and Coriolis flow meters, we measure the mass flow rate or the Doppler shift that happens in the instrument. So by measuring either the differential pressure or the vortex shedding, mass flow rate or the Doppler shift, we correlate that to the flow rate. Vortex shedding is the shedding of the turbulent energy which are created by the vortices in the uh, flow path. So, by calculating or measuring the amount of energy that is getting dissipated, we can we can calculate the mass flow, volumetric flow rate. So that is the working principle of the vortex flow meters. Next is your pressure. The common instruments that will be used for measuring the pressure are the pressure transmitters, then Bourdon tube pressure gauge, then diaphragm seal transmitter. Uh, the working principle of all these instruments will be to measure the force that is exerted by the fluid per unit area. So by measuring the force, we can calculate or we can get the value of the pressure by measuring the force exerted by the fluid per unit area. Next is the process variable of temperature. The common instruments that will be used to measure the temperature or the resistance temperature detector, that is RTD. Then we have the thermocouples and bimetallic thermometers. The working principle of these instruments is to measure the resistance change or the induced EMF generation or the thermal expansion that happens due to the heating up of the material. By correlating these resistance changes or the EMF electromotive force generation or the thermal expansion, we can measure the value of temperature. Next comes the level control, where or the level variable. This is measured by using a float type instrument or radar level transmitters or ultrasonic level transmitters or differential pressure level transmitters. The working principle here is to measure the displacement in the case of float type or radar level transmitters, or the time of flight or pressure difference is another working principle of these instruments. The ultrasonic level transmitter uses the time of flight, and also the radar level transmitter uses the time of flight. So time of flight is nothing but when the level is getting changed, the ultrasonic level transmitter and the radar level transmitter will send out some signals. So those signals will be deflected when the level is changing. By measuring the deflection, we will be able to correlate the level. So that is the working principle in the case of time of flight. Or we can measure the pressure difference. So that is the DP level transmitter or the differential pressure level transmitter. So next is the pH and conductivity. Here we have pH sensors and conductivity meters. The working principle of these pH sensors and conductivity meters is to measure the ion concentration or the electrical conductivity of the solution. By measuring the electrical conductivity and the ion concentration, we can correlate it to the pH values and the conductivity of the solution. So this table is the summary of the various process variables that are measured in the plant, and what are the common instruments that are used for this purpose, and the working principle of those instruments are given in the third column. A very important or the crucial component of an automatic control system will be the final control elements. Uh, they are the last and the most crucial component in the case of an automatic control system. They directly regulate the flow, pressure, temperature, or other process parameters based on the signals from the control system. Nowadays, since the process plants are moving towards automation, the final control elements are the crucial part to receive the signals from the controllers. The controllers will be PLC. PLC means it's the programmable logic controllers. DCS means distributed control systems. Then SCADA is supervisory control and data acquisition. So these are all the controllers which are used in an automated chemical plant or a process plant. And the final control elements are the instruments which will receive those signals from the controllers, and it will act accordingly to maintain the desired set point in a process plant. Suppose if we have a set point of temperature, let us say 60 degrees centigrade. Now the according to that desired set point, the final control element will receive the controller's signal, whether the set point should be maintained at 60, or if there is any changes in the set point, if the temperature is moving higher, let us say 65 degrees centigrade. Now the final control element has to take the necessary action based on the signal from the controller. The controller is going to send out the error signal, that is the difference in the set point and the measured values. Based on that, the controller is going to send the control signal to operate a valve or any instrument or a regulatory system. So the controller's signal has to be interpreted and put into action by the final control element. So that is the last or the most crucial component in an automatic control system. They are used to regulate the process parameters like your flow, pressure, temperature, etc. And it will ensure the process stability by responding to the various control signals, and it will reduce the manual intervention and enable the automation of the process, and it enhances the safety and efficiency in an industrial operation. So the major functions of the final control element will be to regulate, then ensure stability, reduce the manual intervention by enabling the automation, and enhancing the safety and efficiency in industrial operations. So this slide is about the types of final control elements. So before we move on to the types of the final control elements, We look at a flow scheme which is given on this picture. Here you have a reactor which is jacketed. So in the jacket you have the steam passing through to regulate the temperature, and we can see that steam is getting passed through a control valve to the jacket. So here there is the control loop is given in the form of the recorder controller, which will be measuring the temperature. Then M is the measuring instrument to regulate, M is the measuring instrument to measure the temperature, and TT stands for the temperature transmitters, and there will be an element which will transmit the measured value of temperature to the transmitter, and the transmitted value is going to the recorder and controller. Now the recorder controller will compare the set point and the measured value of temperature, and it will send out the control signals to the control valve. Here we can see that from the temperature transmitter to the control valve, the line is represented as dashed line rather than a solid line. So it means those are electrical signals which will be transmitted to the controller. Now the controller will take the necessary action based on these signals, and it will send out another electrical signal to the control valve, so that the valve is either opened or closed to allow some amount of steam inside this jacket. So if the temperature is higher than the set point, then the valve will should close, so that this amount of steam which is going into this jacket should reduce to reduce the temperature inside the reactor. If on the other hand the temperature is reduced inside the reactor, then we need to maintain that value of temperature by providing the heating by the steam, by opening or increasing the flow rate of your steam. So that is the idea behind this control loop. So here the final control element in the case of this schematic will be the control valve. So where is the loop here? The loop is uh, the measuring instrument, the temperature transmitter, and this reactor, and the recorder controller. The final control element will be the control valve that is present here. So now we will discuss the various types of final control elements. The first type of final control element is the control valve. The control valve serves to modulate the fluid flow in the various pipelines. Then on-off valves is another type of the final control element which will fully open or close the fluid flow. Then we have the pressure relief devices which will protect against the overpressure conditions by releasing the pressure in the process line. Uh, the next final control element is the dampers and louvers. The dampers and louvers will control the amount of airflow in combustion or ventilation systems. It will be helping to maintain the ratio of air to the fuel, so that the proper combustion takes place. Next is the variable speed drives, or in short we can say as VSDs. They will control the speed of the pumps and compressors. Next is the actuators. The actuators is a device which will control uh, the mechanical movement of the valves. They will control the uh, movement of the stem by converting the control signals into mechanical movement. The actuators will serve to either open or close or operate the valve. The mechanical movement of the valves inside the valves will be taken care by the actuators. The actuators are the devices that will change the control signals into the mechanical movement. So these are the various types of final control elements. The various types, in short, are the control valves, on-off valves, pressure relief devices, the dampers and levers, variable speed drives, and the actuators. This slide gives you a summary of the various types of control valves that are used in process lines. First is the globe valve. The working principle of the globe valve is to move a plug up and down to regulate the flow. The applications of the globe valve is precise flow control and steam line applications. Next is the ball valve, where you rotate a spherical ball with a hole in the center. That will, when the ball is actually rotating, the opening or the hole will uh, partially be seen or completely it will be seen. So that rotating spherical ball with a hole will control the flow, and it is used for quick shut off and high pressure applications. Next is the butterfly valve, where you have a rotating disc which will modulate the flow. The butterfly valve is used for large flow rates and very low pressure drops. Then gate valve. The gate valve will have a gate that will move perpendicular to the flow to open or completely close. So gate valve is used for isolating the flow, and it is not used in the case of pulsating or modulating flow. Diaphragm valve. The diaphragm valve will have a flexible diaphragm or a membrane kind of an arrangement, elastic membrane kind of an arrangement, where the diaphragm will be stretched or loosened to control the fluid passage, and it is used in corrosive applications and to transport viscous fluids like slurries. And next is the pinch valve. In the pinch valve, we have a very small rubber sleeve which will be pinched or which will be applied pressure on the rubber sleeve, so that the rubber sleeve is pinched to either regulate the small opening between the two rubber sleeves, and when it is pinched it will stop the fluid flow, and if it is the pressure, if it is released, the opening actually increases. So the pinch valve is a rubber sleeve which will be pinched to control the fluid flow. The applications of the pinch valve are used in abrasive liquids and slurry applications. So these are the most commonly type of used control valves. So first is the globe valve, then second is the ball valve, then butterfly valve, gate valve, diaphragm valves, and pinch valves. So we have a detailed lecture on the various types of valves used in the industries. So as far as now, we learn about a very brief summary of the various valves used in the industries. Next final control element is the on-off valve. So here the on-off valve is also called as isolation valves. Why do we call them as isolation valves is because they are used to completely stop or allow the flow of the fluid in a pipeline. Uh, the difference between the control valve and the on-off valve is that the control valve is used to regulate the flow, but the on-off valve will operate in binary positions. That is, either it will be fully open or fully closed. The on-off valves does not serve to regulate the flow. So by regulating means we cannot modify the flow rate in this on-off valves. So there are only two positions of this on-off valves. That is one is fully open position or the fully closed position. When the valve is open, that means the fluid flow will happen through the pipeline without any obstruction, and when the valve is closed, it completely blocks the fluid flow. There is no point of regulating or manipulating the flow rate by means of these valves. And the opening and the closing is actually achieved by either manual means that is by operating a hand wheel or a handle, or by electrical means, or by pneumatic means, or hydraulic actuation. Pneumatic means by using air, then hydraulic means by using a hydraulic fluid. Electric means by sending out the electrical signals to operate the actuator. The example of these various on-off valves will be the gate valve, ball valve, butterfly valve, and solenoid valves. These valves actually help to completely stop or allow the flow. It is not used to regulate the flow. So when the valve is open, it will allow the fluid to flow through the pipeline without any obstruction. And when the valve is closed, it will completely block the fluid flow. Next type of the final control elements is the pressure relief valve. So if you look at the construction of this pressure relief valve, you can see that there is a main body of the valve. So it will maintain the structure containing all the components, and there is a spring mechanism. We can see the spring in the purple color. The spring mechanism will be used to keep the valve closed under the normal conditions, and there is a disc and the seat arrangement which is given by this yellow color and this orange color. So this disc and seat arrangement will be controlling the opening and closing of the valve, and there is an adjusting screw which is given uh, to set the desired pressure limit. Then there is an outlet discharge. The outlet discharge is the line which will release the excess pressure safely. So here the definition of a pressure relief valve is a safety device that is normally used in industrial piping and equipment to prevent the overpressure conditions by automatically releasing the excess pressure when it exceeds a preset limit. The types of the pressure relief valve, it will be the safety valve, then pilot operated PRVs, relief valve, rupture disc, and temperature and pressure relief valves. Then TPRV, that is a short for temperature and pressure relief valves. In the case of rupture disc, you have a small thin membrane, or we can also say it as a diaphragm. If the pressure is exceeded, what happens is the disc will rupture, so that the extra pressure that is built up in the process pipeline will be released by rupturing a small or a very thin disc. So the pressure relief valves are very important safety devices because it prevents the overpressure conditions by automatically releasing the excess pressure. So here you have the spring kind of an arrangement where the spring will be under tension and compression, and by excess pressure the valve seat or the disc seat will move up or down, so that the pressure excess buildup will be released by opening this valve and adjusting the position of this screw. Okay, the screw will actually set the desired pressure limit. Once the desired pressure is exceeded, the valve actually opens, and the excess pressure is let out. So there is a handle here which is used to reset the uh, pressure valve once it is operated to release the excess pressure. The handle will lock this screw arrangement and the spring mechanism under the normal conditions. So once this pressure relief valve is operated to release the excess pressure, the handle will be used to uh, reset the pressure relief valve to the normal position. The next component of the final control element, or the next type of final control element, is the variable speed drives. So variable speed drives are actually connected to the motors which will operate the pumps and the turbines. So here if you see this schematic, you have a pump which is operated by means of a motor. So this motor is connected to a variable speed drive. The variable speed drive will send out the signals to operate the motor at a particular speed. So by adjusting the input power frequency and the voltage, the variable speed drive will control the speed and the torque of an electric motor. So depending upon the speed and the torque of the electric motor, the pump will operate to change the flow rate. So if the speed and the torque of an electric motor is very less, then accordingly the flow rate of the pump discharge will reduce. So this variable speed drive is a regulating device which sends out the electrical signals to control the speed and the torque of an electric motor. So this will be done by adjusting the input power frequency and the voltage. The purpose of this variable speed drive is it is energy efficient, that is it reduces the power consumption, then it provides very precise control of the motor speed, so that depending upon the process requirements it can adjust the motor speed based on the process requirements. Then it extends the equipment life, that is it reduces the mechanical stress on this pump. Next is the input power. So the circuit actually consists of the AC supply, that is the power measurement. Then we have a rectifier. The purpose of the rectifier is to convert the AC current to the direct current, DC current. Then the DC bus will be storing the energy. Then there is an inverter that will convert the DC back to AC signals with variable frequency and voltage, and this will help the motor speed control. The output frequency will determine the motor speed. So the variable speed drive will generate an output frequency to determine the motor speed. So depending upon the RPM, that is the rotations per minute of the motor, the pump operates to either increase the flow rate or to decrease the flow rate. So this is the functioning of the variable speed drive. So which is an electronic device that is used along with pumps and turbines to control the speed and torque of the electric motor. Next is a very important final control element, that is the actuator. The first part of the actuator is the valve actuator, which opens or closes a valve in response to the control signals. The actuator is the part of the final control device that causes a physical change in the final control device when there is a signal which is received by the actuator. So depending upon the signal, the actuator will help to open or close the valve. The working principle of the actuators will depend either on the pneumatics or hydraulics or electrical arrangements, and there can also be diaphragms or bellows, springs, gears, and hydraulic pilot valves, pistons, or electric motors that will be often part of an actuator system. So the most common type of actuator will be the valve actuator. So that will open or close a valve in response to control signals from the controller. So the different types of actuators, they have different working principles. So they will be discussed in detail shortly. The first type of actuator is the hydraulic actuator. So here, if you look at the hydraulic actuator, uh, it consists of a cylinder, piston, spring, hydraulic supply, and return line, and there is a stem. So the hydraulic supply and the return line will have a hydraulic fluid. So here the piston will slide vertically inside the cylinder and it will separate the cylinder into two chambers. So the upper chamber contains the spring and the lower chamber will contain the hydraulic fluid. The hydraulic supply and the return lines, they will be connected to the lower chamber, and it will allow the hydraulic fluid to flow to and from the lower chamber of the actuator. The stem which is connected to this piston will be transmitting the motion of the piston to a valve. So you can see that the stem can actually lift when the spring arrangement is moving upwards, and the stem arrangement can lower so that the opening is closed to uh, not allow the flow of the fluid. So you can see that there is a cylinder with a spring and a piston arrangement. The hydraulic fluid actually moves the piston up by uh, interpreting the control signals. So depending upon the control signals, either this piston moves up or the hydraulic fluid is compressed so that this stem with the seat of the valve stays at a particular position. The force exerted by this hydraulic fluid when moving up or down will be balanced by the force exerted on this spring, whether it is in tension or in compression. So the hydraulic fluid will be helping the piston to move up or down, so that the stem position will decide whether the valve is opened or closed. So this is the principle of the hydraulic actuator. Next, we move on to a solenoid actuator. Here, the construction of the solenoid actuator is, we have a coil, then armature, spring, and a stem. The coil will be connected to an external current supply. So when the spring is resting on the armature to force it downward, the armature actually moves vertically inside the coil, and it will transmit its motion through the stem to the valve. So when the current is flowing through the coil, it will generate a magnetic field formed around the coil. So the magnetic field will attract the armature towards the center of the coil. So as the armature moves upwards, the spring will collapse and the valve will open. So this is, by means of electrical connections, we are generating a magnetic field. So depending upon the strength of the magnetic field, the armature will be attracted towards the center of the coil. So this principle is similar to the generator or the power generator, where you have a coil, armature, spring systems, and you have the carbon rings and brushes, which when the armature is rotating, it generates a magnetic field. That magnetic field is converted to the current by means of the brush and the split ring arrangement. Similarly, here in the case of solenoid activators, you have an electrical connection. That electrical connection will generate a magnetic field. So because of the electromagnetic induction, so when the magnetic field is generated, it will attract the coil, it will attract the armature towards the center of the coil. So when the armature moves up and down, the spring will collapse or release, and the valve opens or closes. The next type of actuator is the pneumatic actuator. The construction of this pneumatic actuator is, you have a diaphragm, a mechanical stop, and there is a supply air connection. There is an upper chamber to place this diaphragm in a proper position, and there is a lower chamber which will house the spring, and there is a local position indicator, a stem, which will move the seat to open or close this opening. And the principle is, it operates by a combination of force exerted by the air and spring force, and the actuator position a control valve by transmitting its motion towards the stem. So when the control signal increases, the valve inside the positioner actually admits more supply of air into the actuator. So as a result, the control valve actually moves downwards. That is, when the supply air connection supplies a greater amount of air, this diaphragm is actually pressed so that the spring is compressed. When the spring is compressed, this stem is lowered so that the seat actually closes the opening. The flow will be stopped. There is a linkage that will transmit the valve position information back to the positioner. So this will form a very small internal feedback loop for the actuator. So there is a local position indicator where the stem is located. So depending upon the forces that are acting on the spring, this local position indicator will move upwards and downwards to indicate the exact position of the stem. Then when the valve is reaching the position that correlates to the control signal, the linkage will stop this flow condition so that the actuator will be stopping. So the spring will be at a particular value of tension uh, so that this stem is placed in the seat arrangement of the control valve. So if the control signal is decreasing, then the another valve inside the positioner will open and it will allow the supply air pressure to decrease. So when the supplied air pressure is decreased, then the diaphragm actually returns back to its normal position. So when the supply air pressure is decreased by venting the supply air, this will allow the valve to move upward and open. So that is the tension in the spring will be actually released. So the spring actually expands. So when the spring expands, the diaphragm moves up to its normal position and the valve will be uh, opened by moving this stem to upwards.